Hello, am I audible?
Good evening, sir.
Good evening. Let's get started. Today's
I have a
session
doubt,
is,
sir.
tell me.
The how to solve the graph theory sums, sir. It's being confusing.
Do you have any particular problem in mind?
No, sir.
Any type of,
Full sums are confusing. The lecture sum is
okay,
okay, but the exercise and graded assignment question is little confusing.
maybe we'll take a few practice assignment questions once I'm done with, I believe, directed acyclic graphs and topological sorting has not been covered, right, in the previous session.
Yes, sir.
Okay. I'll do that first, and then we'll see problems. I don't have a specific set of problems, so if you have any problems which are not in the GA and you can let me know, that'll be better for you. But anyway, let's get started first. So we have two things to cover today. Directed acyclic graph and
Hello,
topological sorting. Yes,
am I audible?
yes.
Okay, thank you.
Okay. So by now I'm assuming you guys know independently what these two terms mean, right? One is what is a directed graph, what is an acyclic graph. Can anyone quickly say what the two things are?
Directed graph is where we have a direction particular from one vertex to another. And
Right. So a graph in general is a set of vertices and edges between them. And if the edge comes along with the direction, let's say something like this, each edge not only tells you what two vertices it is connecting, it also tells you from which vertex to which vertex. For example, this edge from 0 to 1, there is an edge from 0 to 1, there is an edge from 2 to 0. There is no edge from 0 to 2 in what I've drawn. All right. So, and let's do this. Let's do this. This. Maybe we'll just keep this as our example. So this is a directed graph. The arrows pictured better. So let me just make it a little more. So this, 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 and this correct. All right. So you know which way the edges are pointing. Is this an acyclic graph?
No, sir, because it's starts from zero means it's not go and end at zero, so it's not a cyclic. I think so.
Okay.
I think
So
it is acycle because there is no cycle. If
right, so this
we
is there are 6 vertices. So first of all, what is a cycle?
if A goes to B, B goes to C, and C also goes to A,
A
then that is
path which starts and ends at the same vertex. Right? Now, in the case of a directed graph, this will also be a directed path, meaning you cannot travel from 1 to 0, for instance. Only one direction traveling is permitted. Now, is there any cycle in this? Can you quickly just see and say?
no such cycle.
Suppose I had, let's say, another vertex, something like this. With that, will this be cyclic or acyclic?
In that case, this becomes cyclic.
Right. So if I have 0 to 1, there is a vertex. 1 to 3, there is a vertex. 3 to 0, there is a vertex. So I have a path from 0 to 0, a path of 3 edges, which starts at 0 and ends at 0. So this would be a cycle. But the focus of today's session is not paths with cycles, but sorry, graphs with cycles. It is graph without cycles. These are what are called acyclic graphs. In particular, you have seen that trees are acyclic, right? The BFS, DFS tree that you get from the algorithm that is described, you get certain trees. But in this case, this is not a tree, but this is not an acyclic graph. Sorry, this graph doesn't have cycles, so this is an acyclic graph, right? This is an acyclic graph. To properly verify that, you have to start at every um,
Hmm.
vertex and then try to get a path back to itself, which you will see that is not possible. All right. So this is an example of a directed acyclic graph. Also, common abbreviation for it is DAG. So a DAG is a graph which is directed and acyclic. So first of all, why do we look at directed acyclic graphs? These are very natural models for many phenomena. One very nice example is given by the prof. And another thing that you can use your course structure itself to design is a directed acyclic graph, which contains all your courses which are ordered by prerequisites. For example, you can draw a graph with math 1 over here, math 2, stats 1, stats 2. There are others. I'll not write them. Maybe these two together will be required for something like machine learning foundations. I don't know if MLF has more prerequisites, but I'm just giving an example. So, and then machine learning foundations is required for something, some other things which further branch out. So, so this is a directed acyclic graph, right? So why should such a graph be acyclic? So the claim is that a graph which describes I'll just write it as course structure. Should be acyclic. So can you give me a very natural reason as to why that is true?
Because the below vertices can't be
Okay,
opposite
below
go to
and
opposite.
above is just a way to write it. Really, I could have written it as math one, math two, stat one, stat two, something like this, and then so probably you should not use below and above.
I would like to
Sir,
phrase it.
if we know max 1, then we will move to math 2, and next like step process step by step is we can say, sir.
To be more precise, like the future events will only happen if past events has already occurred.
Right. So suppose I'll just write C1, C2, something, CK, C1 is a cycle. So what does this mean? By the description that we have given, it says that C2, the course C2 requires C1 as a prerequisite, and C3 requires C2, and so on. But C1 requires CK as a prerequisite, which in turn requires CK minus 1 and so on up to C1. So you can't do C1 without doing C1, which does make sense, right? Is a cycle. What this would imply is C1 is a prerequisite, prereq for C1, which is absurd. Now, do you see why such a graph has to be acyclic? I mean, this is the proof. Do you understand the argument?
Yes, sir.
Yeah. And this is not just for course structures or anything. Any sequence, or not necessarily sequence, a list of events, let's say, which has some ordering required. There needs to be 2 tasks completed before I can take up this third task, and that has to be completed before I do something. You can always write it in terms of uh, a graph like this, scheduling or ordering of workflow that can always be written in a graph form, which will happen to be directed and acyclic by definition. Acyclic meaning acyclic is not by definition, but it is very easy to see that such a thing cannot have cycles, right? Now, in this small graph here, you can see if you were to be doing this course, you can take M1, S1, M2, S2 in different semesters, or you can do M1, M2, S1, S2. There are different orders in which you can pursue the subjects. And over here, even the branching is very simple. If there are more complicated things, there may be many more combinations. So in general, given a directed acyclic graph, given a DAG, can we determine an order to perform the tasks, or I would say I'm just going to write perform the tasks. But what I want to say is in terms of the graph theory, it is just that is there an order of vertices which we can go through such that if there is a vertex in the list, then there is no vertex which is coming into that vertex, which appears after it, which is the same as saying you can't do the prerequisite later. Prerequisite has to come to the left of. So suppose I do this, I can do something like M1, M2, S1, S2. So this is an order, MLF and so on, and something. This is possible. This is okay. But you can't say have M1, S2. I think for stat 2 also this is a prerequisite. Maybe it is. I'm not sure, but doesn't matter. M1, S2, S1, M2. This is not possible. Why? Because here we have S2 coming before S1. Such a thing is not permitted. So how can I, just using the data from the graphs, either using an adjacency matrix or an adjacency list, how can I come up with an order of vertices in the examples that we have given? The vertices correspond to tasks or courses. So how can I come up with an order such that I can get the task done properly, meaning the prerequisites are completed before the things that they are prerequisites for. So this is what is called topological sort. Topological sorting for directed acyclic graphs. So let's take this example itself. Let's try to topologically.
Sir, I actually
Yes.
missed the last part which you just mentioned about the topological graph. Could you just explain it in one word, in one sentence?
So it's like you want to write a list of vertices in such a way that the vertices which come to the left are always like if I encounter, sorry, if I look at any vertex over here, there should be no prerequisite of it to the right of it. All prerequisites should be to the left. In this case, it is simple to come up with such a thing. But for this is a directed acyclic graph we have seen. Let's try to find an algorithm which can do it in general for any directed acyclic graph. So let's take that graph again. What would be the obvious starting point? Think again in terms of the intuitive.
0, 0.
Can we start at 0?
Unknown. 2.
Sir, the nodes having 0 in degree, maybe we can start with that.
2.
Can we start with 0, 2?
Yes,
Can
sir,
we start at
because
0?
No, because
In degree
uh,
1.
2 is going to 0.
Yeah, so
So
if you have 0 and then somewhere if you get 2, then what happens is 2 is coming to the right of 0. And 2 is a prerequisite for 0, right? So that cannot be done. So the idea was correct. So the answer is no. We have to start at a vertex that has in degree equal to 0. Is this clear why this needs to be done? Otherwise, there will be whatever, if the in degree
Sir,
is greater than 0.
can you please again teach this? I can't understand.
So, okay, so in terms of the prerequisites or the ordering of the vertices that we were talking about earlier, what does a directed edge represent? So suppose I have this edge, right? In this graph, I have this edge 2 to 0. What does this mean? The sorting that we are trying to achieve, we will have to put 2 before 0. Is that correct?
Yes, sir.
So if I start at 0, then 2 will come somewhere later.
Will not come, I think so, if we use 0.
No, if I
Because the
start at
edges.
0, then 2 will come somewhere, right?
No, sir, the directed, no, the edge was not connected for 2. So that I think 2, 0. Is that correct?
No. I'm saying that if I start with 0, so I want, what is my goal? So goal is get a sequence of all vertices such that prerequisites, I'll call them prerequisites. I hope it is clear what I mean by prerequisites come to the left of whatever their prerequisites for. So if I start with 0, the 2 will come somewhere, may not be immediately. So if I want to get a sequence of all vertices, I want to get a chronological list of things that I need to do in some order. I want an order in which I have to perform the activities or traverse the vertices of the graph. So if 2 comes somewhere over here, that cannot be possible because that would trace back to 0 being done before 2, which is not okay.
Okay, sir.
All right.
All right, sir.
So that is why we have to start at a vertex which has in degree 0. What does it mean in terms of the language that we have used so far? What does a vertex with in degree 0 mean?
There should be no incoming vertex.
Meaning we cannot reach to that vertex anyway.
There is no edge between.
Yeah. No. I'm saying, what does it mean? I know you guys know what in degree 0
Yes, sir.
is.
In degree 0 means like there is no incoming
Edge.
vertex.
Right. I'm not saying about it in the graph theory sense. In terms of this prerequisite and whatever task ordering thing that we have said, that the intuitive meaning of in degree equal to 0 for a directed acyclic graph, what does it mean?
There is no prerequisite for that point.
Exactly. So it means there are no prerequisites corresponding to that vertex. Okay, so first of all, there is one result that we have to prove, that otherwise this whole thing falls apart, right? So if what if, so in this case, do you see vertices with no in degree?
2.
Yes, sir. Only 2.
Yeah, there's precisely one vertex which is number 2. But what is the guarantee that every directed acyclic graph will have a vertex within degree 0? Is that always possible?
Sir, I can
What
say
was your
no,
question?
it is not always possible. Maybe we can we can divide that graph into 2 parts. Like one part is connected with each other and the another part is connected with each other, and there is no any connection between those 2 parts. In that case, we can say that like in degree need not be 0 always.
I'm claiming that every directed acyclic graph has a vertex with in degree equal to 0. We'll take a look at your example and see why that either it will not be a directed acyclic graph or some problem will happen, because every directed acyclic graph will have a vertex within degree equal to 0. So what we will do is assume the opposite. So suppose every vertex has in degree greater than 0. Right? So this is called proof by contradiction. We will assume the opposite of what we need to prove, and then we'll derive a contradiction. That means our assumption is false and the result is true. So suppose every vertex has in degree greater than 0. I start out with any vertex V0 that has in degree greater than 0. So there is some vertex V1 such that there is an edge from V1 to V0. Is this okay?
Yes, sir.
Once again, there is V1 also has in degree greater than 0. This is by definition. Not by definition, sorry, by assumption. Every vertex has in degree greater than 0. So I look at one of V1's parents. That is V2. Again, I can do the same thing. I get a V3. I can do this forever because there is nothing stopping me since the in degree of every vertex is positive. So I can always find parents for every vertex. Now, if I have total number of vertices to be n, I can do this for n steps, right? This is step 1, step 2, step n. And I have exhausted. So here there are n plus 1 vertices listed. V0, V1, V2, V3. There are total n plus 1 vertices listed in this chain. But we have only a total of n vertices. What does that mean?
I didn't get like how n vertices is there.
So I can do it for step 1. I'll get a vertex V1, right? I look at V0. It has in degree 1 or more. I get a V1. Then V1 also has, by assumption, at least 1 in degree. I look at one of the vertices which is mapped to V1.
Okay, sir.
That is V2. Then I look at one of V2's parents
Yes.
or prerequisites or whatever. I get V3. I do this for n steps,
Okay.
right? And suppose my vertex set is itself is 0, 1 up to n minus 1. I'm naming it as numbers as we usually do. 0 to n minus 1. There are n vertices, but there are n plus 1 vertices in this chain that I've listed. How can that happen? That cannot happen unless complete this statement.
Yes, sir.
That cannot
Because
happen unless
Vn doesn't have any in degree here.
no, Vn also has an in degree. I'm saying that this is sufficient for me because I have a list of n plus 1 vertices over here, but I actually have a total of n vertices in my graph total. It's a finite graph, which means that there must be some repetition here, right? So I've not asked for the parents to be unique at every point.
Oh, okay, okay.
Is that not correct? Is that clear?
Yes, sir. Yes, sir. It
So
is
I
clear.
have n plus 1 vertices among n vertices, meaning there has to be some repetition. But what does a repetition mean?
Cycle. Sir. No.
That's a cycle. So suppose I have this guy V2 or let's say I have a Vi and a Vj, both of which are actually the same. Vi is equal to Vj. Somewhere in between, I have two vertices to be the same, which I'll just write it as Vi itself. There is a sequence, something like this, Vi plus 1 or whatever until this. So what does this mean? Vi has a vertex, has an edge coming from Vi plus 1, which has an edge coming from Vi plus 2, and so on. When you trace it back, you get Vi itself. So it's like Vi plus 1, Vi plus 2. And if you keep tracing it back, you will come to Vi itself, which is equal to Vj, which is the repeated vertex, which means that there is a cycle.
Means, are you trying to say like Vn is also has a incoming which is nothing but V0?
Not necessarily. I'm just writing a list. I can write this list indefinitely, right?
Yeah.
Because every vertex has in degree greater than 0. I can write it for as long as I want. I chose to stop at Vn, I chose to stop writing at Vn because that will definitely force the repetition of vertices, and that is what I want. If this is confusing, let us just look at these n vertices. There are n vertices over here.
Yes, sir.
Yes.
Well, it need not be V0 always, right? So, yeah, there is a repetition. Assume that that repetition is the V0 coming over here somewhere. What does that mean? That just means that you have started with V0, V1, V2.
There is a cycle.
Yeah, so you have a cycle from V0 to V0. It need not be V0. I'm just taking the easy case where that happens. In general, you might have a repeated vertex somewhere in between. And that the chain which corresponds, which is between those two repeated vertices is a cycle, right? It starts from V2 and ends at V2, and you backtrack. So the upshot is there is a cycle in the graph. But can that happen? Can there be a cycle in the graph?
In DAG, that's not possible because
That's not possible because we have started out with a DH. So this assumption that every vertex has in degree greater than 0 is not possible because that would imply that there is a cycle in the graph, which is not true. Is that fine?
Yes.
This is not possible. Therefore, there exists, this is a symbol for there exists a vertex with in degree equal to 0. So that solves our starting problem, where we started out with a particular graph, but in this case, it was, when we looked at it, it is obvious that we have a vertex with in degree equal to 0, which is 2. But in general, that might not be the case. We thought that there is a possibility that it might not be the case, but this result proves that this is the generic case. Like in every directed acyclic graph, there is a vertex with in degree equal to 0. So what was the example that you were saying that there could be a graph with in degree? There was someone saying that it could have in degree greater than 0. Could you please speak up?
Sir,
Yep.
I am a bit confused in that. I just thought that example, I mean, suddenly comes into my mind. So I was talking
Sure,
about
tell me, let's see. Yeah.
uh, like uh, uh, let's draw two graphs which are
Okay.
not connected with each other,
Okay.
and we can consider that as one graph. So is there any possibility uh, we
No,
can
but
have?
even if you consider each of them separately also, then you will
Hmm.
have this argument will work, right? Once again, you start out with a if everything has in degree greater than 0, then you start tracing it back, and eventually you'll have to come back. Is that not true?
Okay. Yes.
Suppose you have like two parts, two disconnected parts, doesn't matter, right? That same result is true in each part individually.
Okay, sir.
Right? In fact, in each component, in each connected component, you will have at least one vertex of degree in degree 0.
Okay. So if each if every component is cyclic, then what will happen?
No, we are starting out with an acyclic graph, a directed acyclic graph.
No, I'm saying that in that graph,
Mhm.
we have divided into two parts, right? If each part is
Okay.
cyclic,
Then the graph together is cyclic. No, that will no longer be a DAG.
okay.
An acyclic graph should not have any cycles. So if I have a graph like this, let's say a triangle and something like this is not an acyclic graph. This whole thing is not an acyclic graph. This is not a DAG. Give it directions if you want. Something like this. This is not a DAG because this is a cycle.
Okay. Okay, sir, got it.
Okay, so first check is done that every DAG has a vertex within degree 0, and that is where we'll start. The second step is that, let me call that resultant step 1. Step 2 is remove vertex within degree 1, all edges from it. So going back to the example that we have over here, in this case, 2 is the vertex. Right? So what does the algorithm say? Remove that vertex in degree 0. Sorry. Since it has in degree 0, there will be no edges into it, but there will be edges coming out of it, possibly. It could be an isolated vertex also, but then you will be left with another component of the graph. So at this point, my sequence is just 2, and I don't know what comes after 2. I start with 2, I remove 2, and the edges which are coming from 2. What am I left with? I'm left with another graph. The result, which is easy to verify, is that the new graph is also a DH. So removing 2 edges does not change the fact that it is a directed graph. You're just removing a couple of edges. The rest of the edges, the vertices are intact and they are directed, and we are okay. It is still acyclic because if this has a cycle, then the bigger graph would also have a cycle. But we started out with a directed acyclic graph and removed a few edges. That will not change the fact that, I mean, that cannot, removing edges cannot make a graph cyclic if it was not cyclic to begin with. So the new graph, meaning the graph which is obtained by removing the vertex of in degree 0 as well as all of its outgoing edges, that is also a directed acyclic graph. Is this clear?
Yes, sir.
Right now, so I do the same procedure over and over again. Right now, this is a DAG. By step 1, I know that this should have a vertex with in degree equal to 0. Does this have a vertex with in degree equal to 0?
Yes, sir. 0 or 4.
0 or 4. So here you have a choice. Remember that you have a choice. Let us take 0. Okay. So in the sequence, the sorting sequence, the topological sorting sequence, I had 2. Now I will start with 0. Now what does step 2 of the algorithm say? It says when you start with this, you remove 0, you remove the vertex with in degree 0 as well as the edges out of it. Now I'm left with this graph. Right? Once again, this is a DAG, a directed acyclic graph. Once again, this has a vertex within degree equal to 0. In this case, what is the vertex within degree equal to 0?
1 and 4.
4 and 1.
4 or 1. So let's take 1. Once again, we'll just add that over here. The sequence at this point is
Where 4 and 1 are both equally eligible now. We can either take 1 or
yes,
4.
yes. Even over here in this step, you could have started with 4 also, because 4 is also has in degree equal to 0. So now we don't have this. Let's do 1. If I choose 1, then I remove it. I remove the edges out of it. What I'm left with is this graph. Here I don't have a choice. What should my next thing be?
4.
So here there's only one vertex with in degree equal to 0, which is 4, 2, 0, 1. 4. Remove 4 as well as this thing. Now what you're left with is just 2 points. So you can choose 3 or 5 because by definition this is a directed acyclic graph. There are no edges, so there are no directed edges, but a graph without edges is also a graph, and it is sort of trivially directed graph as well as acyclic because there's no edges, there's no cycles. So all of that is okay. I can start out with 3. I remove 3 and the edge is coming out of 3, which is a null set, but I remove it anyway. And then what I'm left with is 5 and then. Since you are removing a vertex at each step,
It
if
could be
you
4-3 as well, means correct, or we need to put on increasing or decreasing number.
no, the order is random as long as the vertex that you're deleting at any given step is of in degree equal to 0, you can choose whichever you want. Just for the sorting.
Okay.
Okay, so this is one possible sequence. Another possible sequence could have been 5, 3 also. I'll maybe keep that over here. Uh, After this guy, we'll be left with this and this. no reason to choose one over the other, but we just follow this convention where we list out the smaller number. So here we don't have weights on the graphs and all that. So that, well, even then, so here we are talking just about directed acyclic graphs. So we just say that we list it in any random order, but at every step, we will make sure that the thing that we are listing doesn't have prerequisites. And a prerequisite meaning it has in degree equal to 0. And this is a natural algorithm, right? So what you do is you start out with something that has no prerequisites. So list it as the first thing to be done. And once you're done with that, you have to, there will be more tasks for which this might have been the prerequisite, but now that the prerequisite is done, it frees up more tasks to do. So then you look at the next layer. You look at the next set of tasks. In which order you do is not relevant. So you can choose any of the tasks which you can now do because you have the first step done as the prerequisite. And then you keep doing this until you exhaust the whole graph. So this is the topological sorting algorithm. Are there any doubts about this?
No, sir.
Now, in terms of how do we do the given algorithm in terms of degree is, let's say we start out with the original graph. Right now, I can write the in degrees of each of the vertices. So another way to look at this thing is, what is the in degree of the vertex 0?
1.
This is 1. This is also 1. This is also 1. This is 0. This is 2. This is 2. Right. So what is written in the brackets is the in degree of the vertex. What you do is, in the next step, as we were saying earlier, you remove this. Maybe we'll copy this one. What you will do is take this, remove the 0 in degree vertex, and update the in degrees now. What vertices will have their in degrees changed?
0 and 4.
0 and 4. So next you take this one, choose 4 or 0, doesn't matter. I'll choose 4 this time. Let's see. It's not going to make a difference. So I choose 4. I remove 4 and the edges coming out of 4, which will make me lose these two things. Now, if I have to update the in degrees, what are the changes that need to be made?
3 and 5 will become 1.
Yeah, both of these will become 1. And then this one will become, right. For this one, there's only one vertex that can be removed, which is 0, which will make this in degree 0. And then I'll remove this. I'll be left with 3, 0 and 5, 0. I'm skipping a few steps because yeah, by now you know what's happening. Now I can remove these two in any order that I want. And the sequence that I get this way is in the first step, I remove 2, then I remove 4. I remove 4, I have to remove 0, then 1, then 3, 5, just listing it out. 240135 is a valid sequence. 201435, 201453, all of these are valid sequences. Just using the graph and the in degrees written on against them, you can.
Sir, it
Yeah.
is confusing. Then how will understand that the answer is wrong? This answer is wrong. Means is
It's
there any?
not a unique answer. So such questions won't be like it will not be asked what is the topologically sorted sequence for this. That doesn't have a unique answer.
Okay, sir.
So it might be asked which of the following are possible sequences. But then you can see, right, like at what point which candidates are not allowed, you can see. So if let's say 210435 is given to you as one of the options, is it possible that this is the topological sorted sequence? Is this possible?
No.
Yes. So in this case, whatever option, so suppose the question is, this is the graph that is given to you. Where is my starting graph? This is the starting graph given to you. What are among the following? Select all possible sequences which are topologically sorted sequence corresponding to this directed acyclic graph. If you have some something like this, have I got all the vertices? Yeah. This is obviously wrong, right? So in this case, it is clear that anything has to start with 2. So this will not be a correct option. But once you start with 2, there are only 2 options. You can have 2, 0 or 2, 4. So 2, if there is an option with 2, 1, that is not the correct answer.
Okay, sir. So, sir, today
Okay.
we will discuss the matrix cardinality.
Matrix cardinality?
No, matrix. We are discussing week 10, right?
Yes, week 10, we have, so there was a summary session earlier where most topics were covered, only directed acyclic graphs and topological sorting was remaining, which I have now covered.
Okay.
Okay. And how do you calculate the in degrees? One comment that I will make.
The incoming edges.
Yeah, so not just from the graph itself. How do you compute it from the adjacency matrix? So usually when you are given the data, it is converted into one of 2 readable forms. It will not be in like originally, even though the data is visual in terms of vertices and edges, you usually convert it to the adjacency matrix or the adjacency list. So the
Sir,
adjacency matrix for, yeah.
so that would be the number of ones in the corresponding column. That would be the in degree.
Yes. So with respect to if so in degree of a vertex is the number of ones in the column of the adjacency matrix corresponding to that vertex. But if an adjacency list is given, it is not as straightforward. You have to look at that vertex in which list it comes, and then you have to keep a tally. You have to keep a record of how many of them have that as its target. So that will give you the number corresponding to that vertex. Finish that. Right. So for this, for example, for this thing again, what is the adjacency list? So you have 0, 1, 2, 4, 5. This is just 1. For 1, you have 3, 5. You have 0, 2, 3. There's nothing. 4, 5, and 5. There's nothing. Right. So if you want to compute the in degree of, let's say, 5, then you see how many times it comes in the adjacency list, and that is its in degree. That is how you compute it from the adjacency list. But the adjacency matrix is simpler, even though the search is more expensive in the sense that you have to go through a larger collection of numbers. So here you'll have a lot of zeros. I'll not write down all the zeros. I'll just write down the ones. So 0 to 1, and 1 to 5, 2 to 0, 4. 3 has all zeros, 4 has 3,5, and 5 has nothing. Yeah, these are all the ones in the adjacency matrix. So suppose I want to calculate the in degree of 3. I look at the column corresponding to 3. How many ones are there? There are 2 ones, and that precisely is its in degree. That is what is written over here. Okay.
So, sir, is there any in degree cardinality also we need to calculate?
If you were to do it this way, if you want to write down all the degrees of this, and then start eliminating, updating in degrees and all that, then you can compute the in degree of each of the vertices and then proceed this way.
Okay. For this graph, what will be the cardinality?
No, in degree is for each vertex. So for each vertex, we have written down the in degree, right? In degree is simply number of edges coming into it. For example, this vertex 2 has no edges coming into it, so its in degree is 0. The vertex 3 has 2 edges coming into it, so its in degree is 2. And so on.
Sir, I just have a doubt. Can I ask?
Yeah, sure.
Sir, directed graph means if there is an S from I to J, is it compulsory that there should not be an S from J to I?
For an acyclic graph, yes, but in general, no. That could happen. It could be that there can be an edge from I to J and J to I.
Okay, so this definition holds for only acyclic graphs, right?
Yeah, the whole what definition? This algorithm.
No, I'm not asking about the algorithm only. Like, suppose consider this graph, okay? This one, the example which you have explained.
Okay.
So Let's draw an S from 5 to 0 and 5 to 4.
Just one minute. Let's bring it back. Example. Now you want an edge from 5 to 0. I'll just draw it like this.
Yes,
5 to 0, right?
and 5 to 4
Okay.
as well.
And 5, 4. Okay.
Yes, sir. Is this still considered as DAZ?
No, because there is 4, 5, 4. That's a cycle.
Oh, okay. 4, 5, 4. Okay. Meaning,
4 to
if
5 to
a
4.
subset if a subset is cyclic, then the whole graph would be called as cyclic.
If there is a cycle, it is called cyclic.
Oh,
A cycle can be as small as you want. As small meaning, so this is a cyclic graph, right? So if you just have two vertices, 0 and 1, you have both ways. This is a cyclic graph.
Oh, okay.
So we have this result, right? That every DAG has something without whose in degree is 0. Does this have in degree equal to 0?
No, sir.
No. Both of them have in degree 1. So this is a very roundabout, unnecessary roundabout way of saying it's not cyclic. But yeah, this itself is a cycle. But now if you have something else over here, I don't care what's going on over here, whatever, this is still a cyclic graph. A cyclic graph doesn't mean the whole thing should look like a cycle or anything like that. If it contains a cycle, it's called a cyclic graph.
Okay, sir.
If it contains a cycle, it's not an acyclic graph.
Okay, sir. But that is not cyclic, right? I mean, it is not necessary that the whole graph is
Is
a
there
cycle.
a term called cyclic graph? Is that standard terminology? Yeah, it is seems like it's a standard terminology. A graph that contains at least one cycle is called a cyclic graph.
Oh, okay, sir.
I got confused between the adjacency list and the matrix. If you can go slow on that.
Okay, so adjacency matrix, what do the rows and columns of the adjacency matrix correspond to? What does the number of ones? So when do you write ijth entry?
When there is an incoming edge to it.
Of the adjacency matrix is 1 if and only if
There is an
what is the state? Yeah, there is
an S from I to J.
I to j. So since this is the adjacency matrix of a directed graph, it is important to say from where to where. You can't say there is an edge joining I and j. That does not give you the information about the direction. So there is an edge from I to j. So this is important. So if I look at all these entries, for example, I focus on a row. What are the entries in the row? What are the coordinates of the entries in this row? They are of the form 2, j, right?
Yes, sir.
All of these things, this is 2, 0, this is 2, 1, 2, 2, 2, 3, 2, 4, 2, 5. Now, what does it mean to say that row corresponding to 2 has, I'll write it in words just to be clear, 2 ones. What does this mean?
That is, there is edge
Meaning,
which is coming to 2.
no, which
It's
is
not coming
going to
to
2.
Acha,
Going
sorry,
from
yeah,
2.
going from 2.
Yeah, there are this is the same as saying there are two edges. I'll write it as starting at or starting from the vertex 2. So rows, the number of ones in any row in the adjacency matrix are number of edges coming out of it, which is the same as saying that out degree of the vertex 2 is equal to the number 2. Is this fine?
Yes.
Now the same thing, if I look at columns, what happens? Suppose I focus on this column 3. What are the coordinates of the entries in that column?
1 and 4.
No, here we said that these are of the form 2 comma j, right? So if I look at a column, what are the entries over there?
I,
comma 3.
comma 3.
Yeah, this thing is not part of the example. This is just separate. Now, if I look at things like I comma 3, these are entries in the column corresponding to vertex 3. Now, column corresponding to 3 has, once again, 2 ones. What does this mean?
There are 2 incoming edges at
Yeah,
3.
there are 2 edges ending at or coming into at 3. But is that not the same as saying in degree is equal to 2? In degree of the vertex 3 is equal to 2. So number of ones in a particular column gives you the in degree of the vertex of that column. Number of rows, number of ones in a particular row give you the out degree of that vertex. You can verify it in this specific case. For each of the vertex, you can do it. But how do you write an adjacency list? You just write against 0, you will write what are all the vertices that start at 0. So you write the endpoints of the edges starting from 0. In this graph, there is only one edge which is going out of 0, and it is going to 1. Similarly, if you look at the vertex 1, there are 2 edges going out of 1, and they end at 3 and 5. Similarly, 2 goes to 0 and 4. There is nothing starting at 3. There is vertices 3 and 5 are targets of edges which start from 4 and 5 again. There is no edge coming out of 5. So there's nothing in the adjacency list against the number 5. Now, if I have to, let's say, count the in degree of the vertex 4. If I want to count the out degree, it is easy. I just look at whatever is there over here, the number of entries over here, that would be the out degree. But how do I look at the in degree? For that, I have to look at this side of the adjacency list and see how many times 4 comes over here. It comes exactly once as the target of an edge from 2. So in degree of 4 is 1. Let's say 5 now. 5 appears twice. So the in degree of 5 is 2. So these are, if you're not given the graph and if you're given just the adjacency list of the graph or the adjacency matrix of the graph, you can still compute the in degree and then go on to do the topological sorting. All right, you can reconstruct the graph from the matrix, or you can reconstruct the graph from the adjacency list. And then you can do sorting. So this is all I have. Are there any doubts?
Can we ask from the assignments?
Yeah, sure. You'll have to tell me the question
PA question
entirely.
number 3. PA question number 3.
You'll have to tell me the question. I think the thing is not opening.
Okay. Let V1 is equal to Shishti, Shiva, and Nia. So there is a graph. So I can't iterate that graph. So it would be better if you can,
Let
take
me
a
see. Very yeah, it has opened now. Just one more. You have V1 is equal to a 3-element set. E1 is there is okay. There is a common question for this, is it? Okay. Okay. So what is the doubt? What seems to be the problem?
I wasn't able to approach this. Like how to solve.
Okay. So you're given a certain vertex set and a certain edge set. Initially, you're given a vertex set V and E, a graph V and E, and then you're asked to consider this what is called a subgraph. You're only choosing certain vertices and certain edges from it. I don't know if everyone has the same set of questions. But V1 is a 3-element set. Since there are no other K, S, and N, I'll just call it. Okay, there is Karim also, but okay. S, N. Now, what is E1 given to be? E intersection V1 cross V1. Right, sorry. It is also described that this is the subset of edges with both endpoints in V1. So if you look at the original graph, maybe I'll just draw the original graph. Yes. Yes. I'll draw it very roughly. This is Joe, this is it's something like
You can cut paste here, I guess.
this one. Okay, this is both ways. Just let me know if I'm making some error.
Just to avoid the error, you can cut the graph and paste it here through sniping tool.
Aha, but that's on my system and here I'm on my tab. So let it be. Let's just work with this. Now, this is the graph given with vertices having certain names. What is E1? So you have a set of edges. What are the edges with both endpoints in V1? V1 comprises of this S and N. right? What are the edges which have both endpoints in V1? V1 is just a 3-element set. Right?
3-element only.
V1 is a 3-element set. What is E1?
Even
Can you
is
list the
also 3
elements of E1?
Yes. Here.
Sir, that would be KRS and NS.
Care. No. We'll repeat it, right? Twice.
Yes, that's it, I guess.
Why do we repeat it?
Because there are 3 elements, right? K, S, and N.
No, we are not interested in this set itself. V1 cross V1 has all elements like KR, KR, SS, NN, KRS, KRN, all these combinations. There are 9 elements in total. But we are taking the intersection with the given edge set also. The given edge set has, among those candidates, only this and this. Only this edge, the edge from KR to S and the one from N to S. So those are the only things that we will list.
Please repeat what you said.
So you were saying that these things like this also should be considered?
Yes, if we are looking V1 into V1 and then
In so if you have this is in V1 into V1, that is correct. Belongs to V1 cross V1. But does this belong to E?
so do we have the element of E?
So E1 is described as E intersection V1 cross V1, meaning you have to look at elements which are both in E as well as V1 cross V1. But KRKR is not there in E.
Okay.
Intersection means it has to be in both of them.
Yeah. Yes,
Sir,
correct.
Right. In general, we don't consider graphs with loops. So such elements will never be there in the edge set. But for a more non-trivial one, look at the element KRN. This is there in E. Sorry, this is not there in E, but this is there in V1 cross V1. Therefore, KRN does not belong to E intersection V1 cross V1. Is this fine? This is just an example. But if you look at this description of the edge set for the graph that you're going to draw, possibly the graph that you're going to draw, it is the subset of edges with both endpoints in V1. So you look at this whole graph, and there are other vertices, I don't care about them, right, at least for this question. I'm just looking at these 3 points and the edges in the original graph, which start and end at vertices within this 3-element set, KR, S, and N. How many such edges are there? There are only the 2 that we have listed, KR to S and N to S.
Agreed. 2 edges.
Right? So it's not, maybe you have a little bit of practice is required to put things together. Like edge set is written as an intersection of 2 sets, and it might get too many layers, but do it step by step. Understand what V1 cross V1 is, what E is. E is also a subset of V1 cross V1, right? Sorry, it's a subset of V cross V, since it's a directed graph. So you're taking intersection of 2 sets. That set is exactly the set of edges for which the vertices are, both endpoints are in the given vertex set. So now you know V1 is KRSN and E1 is, instead of that set theoretic description, you have an explicit description. KRS and NS, was it? Yeah. Can you draw what this corresponds to now? If you're given the vertex set and the edge set, can you draw the graph?
Yes, sir.
It's basically just KRS and N. And then I have a vertex from KR to S and into S.
But how do you define the direction here?
Directed toward S.
Both are directed towards S, right?
Here
So
we
now can you
can
answer the question?
consider here S has two incoming edges, right?
Yes. So why did I draw the direction like this? Because I don't have SKR. Does SKR belong to E?
No.
Does not belong to E. So that's why it does not belong to E1 also. That's why this direction arrow is not there. So the only direction I have is towards S. So in degree of S is 2, out degree of KR and N are 1 each. Everything else is 0. All that is clear, right? So now can you answer the question? So this
It's a
is G1.
directed graph.
And is that the correct answer?
Yes, a directed graph.
Right. Any other doubts?
Sir, I have a doubt regarding that vertex coloring and independent sets.
Was that explained more than just, out of interest, just to tell you what sort of graph theory problems? Is there any result that is explicitly stated, the coloring problems or independent sets? No, right?
Sir, I mean, I'm sorry, like I didn't get you.
No. So I think in the first two videos, Professor Madhavan has explained certain things
Yes,
which graphs arise as a natural model for, and what the problems that we consider in graph theory, where they come up in practical problems. But I don't think that is explained any more than that. So I will take this question if you're interested, but maybe more of the syllabus questions first, if there are.
Okay, sir.
Okay, if there are no more questions, then yeah, you can feel free to ask. What is it about coloring and independent sets that you wanted to know?
Could you please scroll up? I have a doubt here. Could you please scroll up?
Yeah.
Okay, here we are talking about set where which is KR and N, and which is not in part of this E intersection V1 to V1. Yeah, the base
Yes.
down. Yeah. So when we talk about, let's say that we try to draw an edge from KRN, which will be a directed graph towards N, if I'm understanding right.
This would be an edge. Yeah, this is not there in the original graph. Yeah.
Okay. And when it comes for the V1 versus V1 time V1, that part
Right.
I'm not clear about it because like maybe I have missed something what you explained or something I'm not clear about it. Could you please explain that
No, no,
further?
V1 cross V1 is just the whole Cartesian product, right?
Okay.
So V1 cross V1 is is just KRSN cross KRSN. So you'll have like 9 elements
Yeah.
out of this. So this is one set of 9 elements, and the edge set is precisely KRS, NS, and there are all these other guys. There's I don't know how many edges. You can count them. That is another finite set. You're taking the intersection of the two. So if you look at just V1 cross V1 visually, you look at KR, S,
Mm-hmm.
N,
Yeah.
you will have edges between KR and S. You have edges between this, and in both directions in all these. And well, you'll also have loops, edges between uh,
Simple.
from KR to itself and to itself, S to itself. So this is not V1 cross V1. The kind of graphs that we consider, this is not among them because we have to avoid loops, because you'll have elements of the form KR, which is an edge starting at KR and ending at KR, which means it's a self loop.
Yeah.
So this is V1 cross V1. But what we are interested in is E intersection with V1 cross V1. But what was E? E are only the tuples which are present in this graph.
Yeah.
Right. So KRN is not there, for example, in this graph. SN is not there. SKR is not there. There's only two. Among the 9 possible combinations between KR, S, and N, there are only two which are there in E as well, in the original graph E, which is KRS and NS. So that is what we take and write it as E1 as per the problem statement. It is E intersection V1 cross V1.
Okay. Okay. Thank you.
Okay. Yeah, you can ask your question now about
But
independent sets or
if we
coloring.
but if we think in terms of coloring here, can we actually extrapolate this question towards coloring also?
How so?
In the sense, in
I
terms of color, because like if I try to understand in terms of coloring how it, so it again it won't be colored anywhere, or
Coloring
for the
happens
coloring.
only for indirected graph, I guess, not for
Yeah, we generally talk
direct.
about it for undirected graphs. But you can just look at a directed graph and look at the underlying undirected graph and see that as well. But yeah, it's more useful in undirected graphs. So for
Can we
example, you
always,
can
sorry, I
go
interrupted.
ahead. No
Can we
problem.
always use the equation like if you want to find the minimum vertex cover or the maximum independent set? So we always use this formula like number of vertices is equal to minimum vertices cover plus maximum independent set. Does this
You
always
have
holds true?
Is this formula covered?
No, not covered, but I have got this from a book through internet. Just wanted to
Okay.
check, is it safe to, approach the minimum vertex cover and maximum independent sets problem with this?
Are you given problems from those topics?
Yes, there were problem like to calculate the minimum vertex cover or compute the maximum independent sets.
Okay, I'll check with because if such a what we say is if it is not there as a part of what the prof has covered, then so he has just mentioned it in passing from what I've seen. He has not explicitly mentioned this formula, but this is the exam questions. You will not be restricted on the method that you use as long as your source is legit and the formula is correct. If you're getting the answer, it's fine. But can you point me to questions which have these applications?
You may check the practice assignment question number 5 and question number 9.
Okay, okay. I think this particular example of 5, the prof has actually covered in his.
Sir, in
Okay.
the content, this kind of like formula is not there.
It's not there. Yeah. I'll clarify this. I'll make a discourse post probably regarding this.
I agree that the formula is not there, but I wanted to come up with a like more generic a mathematical solution or a formula kind of thing. You know, if the graph or the figure gets complicated, so in that way, graphical or mathematical approach is more better than approaching it graphically.
Right. That's why we try to formulate things algebraically rather than this.
Sir,
But
have
okay,
math
regarding
too.
this, sorry.
I think somewhere because I was just browsing, I think we have something similar to this in Math 2, if I'm right.
Graph theory is not there in math.
Somewhere, maybe I have gone through some of the videos. I don't know where it popped up. I saw some. It's an older version of something.
Math 2 doesn't have graph theory. It has only linear algebra and calculus.
Go through that video once.
sir, linear algebra meaning those like vector spaces and all, right?
Yeah. No, we are digressing a lot.
Okay.
Sorry about that.
No problem.
Sir, can I ask now that
Yes, sure. Please go ahead.
sir, suppose
Regarding this use of things to do, use of other formula, I'll talk to the others and I'll let you in some time in the next session. Maybe I'll get.
If you go to the question number 9 or the PA question number 9, if I may ask.
I saw other questions as well. Yeah.
Yeah. So the vertex is here 8 and the minimum vertex is 4. So the maximum vertex becomes 8 minus 4, which is 4.
Okay.
By
So
that.
yeah, possibly the problems that you have been given over here, you will be able to solve just using the definition, and that's fine. You will not have to resort to using formulas which are not covered. This much we can guarantee. What is the maximum independent set, minimum coloring? All of this is there in what the prof has said, and that will just the basic definitions will be sufficient to answer these questions. Right. Okay. Now, other questions?
sir, in that independent sets, suppose we are given a graph, right? And we can have we can have multiple independent sets, right? From that graph. It's not unique, right?
Just one moment. Independent sets. You can have multiple choices, yes.
Okay. And in those choices, the number of vertices should be fixed, or it like we can have some different type of different number of vertices in each of
Just
the
one minute,
sets.
just for fix. So if I have, so are you asking if every independent set has the same cardinality? Is that your question?
Yes, sir, exactly.
Okay. So if you have, there is something called a bipartite graph. Have you heard of this thing? You can see more of it. If you want to see, you can see bipartite graph. So suppose I have 4 vertices on one side and 5 vertices on the other side, and I just randomly map certain things to certain things. Okay, something like this. Now this is also an independent set. This is also an independent set, right?
Correct.
Because there's no so a bipartite graph is something where you can split the vertex set as a disjoint union of two subsets such that each of them is an independent set. There is no restriction on the cardinality of V1 or V2. This is the easiest way to see that what the cardinality of any independent set need not be unique.
Okay, sir. And
And
sir,
furthermore, just one moment, it is just an independent set by definition is just something which has no vertices amongst its own vertices. So if you have a vertex set as an independent set, any subset of that will also be an independent set, right? So simply independent set will not uh, lead to uniqueness of cardinality.
oh, okay, sir. Meaning, if we take an independent set, if we take the subsets of that set, then that would also become independent, right?
By definition,
So,
right? So yeah.
so it is not fixed, basically. Then, sir, like what is the algorithm to find the maximal independent set?
The question of can you restate the question of maximum independent set?
Uh, mm, uh, no, actually, I solved the activity question, activity 2.
Okay,
Uh,
okay.
so in that
Right.
question, I like the last question, the second activity, last
Activity.
question.
Okay, okay. It's the AQ 9.2.
Yes, sir.
Last question.
So not 9, I guess
Oh, sorry, sorry.
10.2.
10. Yes. The last question or the second last, which one did you say?
The last question that
The
was
last
based
question.
on
Okay.
the independent
Okay.
set.
For instance, sports team, this thing. Where the nodes are the events, okay, and the edges connect. Connect pairs of sports where the teams share a member. The college members, maximum number of sports. Yeah, what's the question about what's your doubt about this?
Sir, actually, like I was able to solve the question, but like while like on the first attempt, I found an independent set having cardinality 4 or 5, but
Okay.
later I got the answer as 6, and
Okay.
at the end I am like I was not sure what is the right answer. I mean, if in the options there would be given something like 8 or 7, some more options will be given. How do I make sure that this is the correct answer?
Okay. Okay.
Is there any algorithm to find the maximum number of vertices in the independent set?
Not that I
That
can
was not there
remember.
in the lecture actually. I
Okay. Okay.
gone through that.
Mhm.
But questions are based on this, so like how can I make sure that this is the right answer, that this is the maximum number of vertices in the independent set?
I do not recall from memory if there is an algorithm to determine the maximum independence set, the number or whatever. So this is just maximum independent set is what you have to calculate, right?
Yes.
Intuitively, it would I would start out with vertices which eliminate minimum possible edges when I remove them.
Okay.
Where, like lightly connected, like all the outside edges, they would only cause one clash, right?
Mhm.
So I can remove those 4 vertices on the outside, which have just degree 1. So if the degree of a vertex
Mhm.
is
Less, right?
less, then that should be considered. Like this is still not an algorithm, but it is.
Okay, sir. Like we can first take those leftmost 2 vertices, right? In that way.
Yeah. Yeah.
And then we can take the rightmost vertex, that the upper right one.
Yes.
Okay, sir.
Then you have to remove all the edges as well as its edges, meaning all its neighbors also, because you can't select its neighbors.
Exactly. We have to eliminate the neighbors. We cannot take that into
Yeah.
the set.
Yeah. Then you'll be left with just a 4 vertex set, not even 4, a 3 vertex set. Once you remove the first 4, at least in this case, in this problem, that is how I would approach it.
Okay, so
I'll have 1, 2, 3, 4, 5, 6. But is there an algorithm? This also I will clarify, and uh, I'll ask and I'll clarify.
okay, sir. And like similar to this problem in the case of vertex coloring also, just
Mhm.
just before that question, the second question,
Right.
the third question, sorry, that is based on the vertex coloring, right?
Question 3.
Yes, sir.
Is it? Computers. What is the preamble? There should not be clashes, so there should be a coloring problem.
Yes, sir, exactly. And here
Yeah.
also it is asked about the minimum possible coloring, like the same
Right.
thing I faced, like while doing in the first attempt, I got some more
Okay.
number, like 4 or 5 as the answer, but
Okay.
later I found that it should be 3. So for this also, is there any algorithm, like how do we
So if
solve
you
it?
want to do minimum coloring, you have
Mhm.
to take a vertex with very high degree,
Okay.
because if you assign one color to that,
Mhm.
that color cannot be assigned to anything else. So it's all of its neighbors can be given another color. So you're covering, at least in the first step, lots of different colors,
Okay.
lots
Okay.
of different vertices with just 2 colors.
Okay.
Once again, a very naive algorithm. or it's not even an algorithm, it's just a naive idea.
Mhm.
So for vertex cover, you were looking at vertices with very small degree. So here you have to look at vertices with very big degree, and that will usually. So which is the correct graph among the four options for question 2?
The correct one is last option, 3.
Last option. So I would start with uh, the vertex with degree 4, either of them.
Sir, but no vertex has degree 4 here. Actually, so the correct graph is the third one. I mean,
Oh, third one.
in the
Okay.
previous question.
That's what I was asking. Okay. Okay.
Uh, so maybe we can like first of all we can give a color to some vertex, and let's say the color numbers are C1, C2, just like that. Then
See, and then there are certain things like cycles. Like if there is a 3 cycle, it should have 3 different colors,
Mhm.
right? So you
Mhm.
have 2 3 cycles in there. It should those 3 should have 3 different colors, but those are disjoint cycles, as in those cycles have no point in common. So I can use the same 3 colors for both of them.
Okay, okay.
Okay, and
Okay.
then there is one vertex which is not part of the 2 cycles, which is connected to both of them. Now, whatever C1 and C2 I have for the vertex coming from the cycle and joining to that other point, I can use the other color. So this is 3 colorable.
Okay, okay, yeah, 3 color. Uh, so maybe like the way I followed that, I randomly chose a vertex and colored that one color, let's say C1,
Okay.
and then
Okay.
then I considered all those vertices which can be colored with C1. Like first
Not immediate neighbors. Yes.
yes, sir, exactly. Let's say
Okay.
I have colored a vertex C1, then I'll eliminate all those neighbors, and then I consider another
Yeah,
vertex.
this is what I was saying earlier also.
Oh, okay.
Uh, that you just look at how many neighbors. If you have maximum neighbors, you can. Okay, I was saying something else. You are saying that C1 and then trying to do C1 again on the outside.
Yes, sir. The possible vertices which we can color with C1. And then we'll select one more color, that is C2. And we can select all the vertices which can be colored with C2. Like if we will select C1, C2, C3 first, then we might get confused uh, at some later point.
Okay. So I don't think there is a very easy algorithm. This is still a very important problem in graph theory. I don't think there is one way to do it for any uh, given graph. There's no things like the BFS or the DFS where you start out with the vertex and then you have this step-by-step procedure. I don't
Yes,
think such a thing exists for graph coloring.
yes, sir. I mean, in BFS, DFS, the algorithm is given, but here, like no
Yes,
algorithm is
I
given.
don't. I don't think there is an algorithm. Is what I'm saying. Yeah.
Okay, okay.
Uh, because graph colorability, even this is a big result that every graph is four colorable.
Mhm.
That is a very deep result. So I would be surprised if there was a general way to determine the minimum number of colors for any given graph. But there are certain things that you can, by practicing more problems, you can see that when there are 3 cycles, you have to have all of them on different colors and stuff like that.
Okay.
And anything that you find convenient, like starting out with something and then looking at the non-neighbors of it, and if there are no edges in between, then you can give them that same color, and so on. All of that you can do, but I don't think there is. But I I'm not sure. So both algorithms for all of these things, independent sets or vertex cover or graph coloring. If there are any, I'll look it up. I'll talk to others and I'll see if there is something that can be said in Gen.
Okay, sir. Okay.
In the next session or the session afterwards, I'll give you more clarity.
Okay, sir. Okay, sir. Thank you.
All right. If there are no more doubts, we'll wrap up.
I have a doubt before you close the session. With regard
Yeah.
to the, we received the main regarding the syllabus for the interim, but when it comes
Okay.
for the weightage, even though I understand it from 1 to 12, is there any special weightage that will be given from 9 to 12?
9 to 12 will be of more weightage than 1 to 8, at least per week. I don't know the exact split.
Will it be 80-20, 60-40?
I think it'll be closer to 60-40. It even maybe closer to 50-50 also. I'm not sure. One thing is, yeah, once again, you remind me in the next session. If the exact number is something that can be given out, and if I get to know it, I'll let you guys know. It is more focused on 9 to 11 content. How much precisely, I don't remember now. So I'll, once again, that is for the next session. And closer to the exam, a post will be made on this course also regarding the same.
Thank you. Thanks.
All right then. See you guys. Bye-bye.